So now I would like to introduce our next speaker, Dr. Jon Peddie. Very pleased that Jon agreed to be here to speak with us today. Jon is the foremost analyst in graphics and GPUs. And your slides must be on the next page, huh? Okay, there we go. So let me see. Jon is, people say often they throw around words like pioneer, but Jon really is a pioneer of the graphics industry. He formed his very well-known firm, Jon Peddie Research, to provide consulting and market forecasting services. He speaks around the world at many conferences on graphics technologies and emerging trends in digital media. He's been named one of the most influential analysts and regularly advises investors and is quoted in the trade press and business publications. He's been a past president of SIGGRAPH Pioneers and is author of several books. His most recent is called The History of Visual Magic in Computers, which I'm very much looking forward to reading. So the reason I asked Jon to be here is Jon's the man when it comes to GPUs and graphics, and as Peter pointed out in his presentation, GPUs are no longer just for graphics. They're also being used for lots of other things as sort of general purpose data parallel processors, and often these days that's for vision. And I think it behooves all of us to understand what's going on there, what's driving that trend, where things are headed, and I think Jon's ideally situated to clue us in on that. So Jon, welcome, thanks for being here.
Thank you. Is this thing working? It scratches. Yeah, so I think the previous Jon gets the choreography prize because I'm not going to move around either. So I don't know what more I can add to what Jeff just said. We are a technical market research firm. Many of the members of this organization are our clients like Peter and Neil and others and so forth. We do bi-weekly reports, we do custom reports. We actually test these things to see if they live up to their promise and so forth. So I've slowly learned over the years that if I tell people up front what I'm going to talk about, sometimes they pay attention. Or at least they pretend to pay attention. So there's four things that I really hope that you guys will leave with, and that is that the increase in pixels has been phenomenal, both on the input side and on the output side. And in between those two, there used to be a lot of specialized processors. There still are a lot of specialized processors, but more and more, there is this thing called the GPU, Graphics Processor Unit, which is a relatively new device. It came to life in the early 2000 time period, and it's still finding its way, so to speak, and every place it goes, it just does remarkable work. And then vision systems will exploit this. The parallelism, the natural parallelism in visual systems is just unquestionable. And so the opportunity for exploitation of the GPU is terrific. And then the last thing is a couple of ideas of what I think is going to happen in the future. So rise of pixels. So if you think about it, we probably first started talking about pixels way back when IBM introduced VGA. VGA was the first widely commercial implementation of a bit-mapped display. There were, experimental things before that, CGA, for example, and of course, there were things in image processing and in machine vision that we're doing. But for the consumer, it was VGA when they started to learn that pixels are discrete little quantums on our screen that have a value of color and brightness, and that means something to us. But we still, as consumers, at all levels, including this room, don't have what I think is a full enough appreciation for what it means to have a lot of pixels. And the lot of pixels is measured in megapixels. Now, I don't know how well this is going to look.
You can see the difference.
Can you? Yeah, okay, good. This was not a trivial picture to make, because what a lot of people will do is they'll just do a boundary size and talk about different resolutions. That doesn't give the answer. The true answer here is there are fewer pixels in this picture than there are in that picture. And if the projector is good enough and your eyesight's good enough, you'll be able to see that things are not quite as clear on this side as they are over there. That's great. So one of my tenets, one of my laws is the more you can see, the more you can do. And I live this and I breathe this. I sit in front of 8 megapixels every day when I'm in the office, and that's not enough. The important thing here is, excuse me, is that all of these pixels are not just two-dimensional items, they're three-dimensional items. They have a color depth associated with them and all. And the color depth is a minimum of 24 bits and can be as high as 48 even, depending upon your system. That's a lot of bits. And that screen is getting refreshed a minimum of 30 times a second. So I'll give you a second to try and process that math, and then I'll save you the trouble and do it for you. So how do we deal with all those pixels? And this was a problem that was first dealt with or encountered or questioned in the graphics industry, because we had to create all these pixels and we had to do it really, really fast. We had to update them quickly, and there was just so many of them, and we could see the trend curves that there was going to be many, many more. How do you do it? And that's how the GPU came about. The GPU is, as Jeff pointed out, a parallel processor. And it's a parallel processor because we need to throw all those pixels up on the screen at the same time. This is a typical, there's multiple examples, but this is just a typical array of what a modern GPU looks like. And this number is not made up or an exaggeration. This is what these things do. And this is how fast they do them. That's teraflops, floating point operations per second. That is a genuine supercomputer. 4 or 5 years ago, to get 4 or 5 teraflops, you would pay $400 million. Today, you can go to Fry's and get this for $400 or less. That's the way the technology's been moving. We thank Moore's Law for that. And so we have all of these processors that are basically moving pixels to the screen. Lately, they're going to be taking pixels from the screen. Now, when they're moving pixels to the screen, they primarily use an API called OpenGL. When they take pixels from the sensor, they're going to use an API called OpenCL and another API, which Neil's going to tell you about later, called OpenVG. And this is where the opportunity comes to exploit the parallel processing capability of a GPU for vision applications. So Jeff asked me if I would spend a few words on what is a parallel processor and how we can use them. The concept of parallel processing pretty much started my career. Started in the 80s. I'm trying to think back how far it goes, but let's say the early 80s to just put a marker in the sand. And back in those days, the idea was already realized that we weren't going to be able to scale quite as quickly as we would like to, and the solution was to try and spread out. So instead of scaling up, we would scale out. And the difficulty then became, and God, I don't know how many PhD papers were written about a thing called crossbar switches. And the idea was that we'd have memory here, we'd have processors here, and somehow or other we had to get those things talking to each other. It was basically a telephone switching network that would allow processor A to talk to memory C, then talk to processor B, and so forth. Now all that's been condensed and consolidated into a system. But in the process, we created names for it. And one of the operations is SIMD, similar or same instruction, multiple data. And it's an easy concept to think about. And it is totally applicable in graphics. Basically, you're going to take all those processors. Remember the previous drawing where we had, I don't know how many thousands of processors. And you're going to tell each processor, all I want you to do is add 2 numbers together and give me an answer. That's all. I don't want you to do Fourier transforms. Just add 2 numbers together and give me an answer. But I want you to do it a lot. And I'm going to feed you this data, and all you have to do is add these 2 numbers together and give me an answer. That's the same instruction, add the 2 numbers together, give me an answer, but I'm going to give you a ton of data. Well, the ton of data is what comes from the sensor. Or the ton of data is the image that I've created in memory from a program, say a CAD program or a game or something like that, and now I want to throw the pixels at the screen. So SIMD, you'll hear the word, in fact, there's a thing called selective sensitivity. you are now all impinged with the word SIMD. You're going to hear it everywhere after today. You'll say, God, I never knew it was such a common word. So you'll hear that all the time. Now, I don't know if you guys follow codecs or not, but codecs is another prime example of parallelism. MPEG is nothing but a big parallel processing problem, and it falls nicely into GPU. In fact, when you do MPEG and when you do transcoding, one of the things we found is that if we try to transcode on a CPU, even a multi-core CPU, for example, we could do it, and it would take X amount of time. Let's say it would take a minute. You could take that same image, that same file, and transcode it on a GPU and do it in seconds. That's the type of acceleration you can get due to parallelism because of the parallel nature of most codecs. Well, remember, codecs are on the front end as well as the back end. So many ISPs, image system processors, signal processors, have a codec that they're feeding. So this is just the basic von Neumann architectural. I don't know how well that, it doesn't look so good in this screen. I don't know if you can see it back there or not. But this is the basic, system that you've learned. I mean, everybody here has probably studied computers, and so you know that you write the memory, you do an arithmetic operation, you put the answer back in memory. And you do it in a stepwise function, ka-chunk, ka-chunk, ka-chunk. In a parallel processor, you do it bam at the same time. So basically, you do all the math and the memory reads and writes at the same time, as many as you have processors for. So now our registers over here now become multiple registers because these are now the processors, the parallel processor we have. So the idea is that that's where you get the acceleration, is in one clock cycle or 2 clock cycles, we can do an arithmetic operation and read and write to memory. And so your acceleration is a function of how cleverly you've written your code, and number 2, how many processors you have to deal with. So how do we use a GPU in a vision pipeline? And this is, everybody's got their model for what a vision pipeline looks like. This is, I think, the most common one. And it can be a closed loop. And I think Neil's going to tell you a little bit more about how it can be a closed loop with VX and so forth. But basically, you're going to take in your sensor. This is where all the pixels are captured. And remember, they're not two-dimensional here either. They're coming in as 3D pixels because they've got color depth. The color depth is done through a Bayer filter of some type. Then you do pre-processing. Then you go into an image signal processor. I was a little surprised that Peter didn't beat his chest more about Raptor. That's their new image signal processor, which is pretty extraordinary, I think. And then after you've done that, then you can post-process and then ship it off to somebody who would like to either store it, record it, or put it up on the screen. But that's the basic loop there. So where could you use a GPU? Well, you could use it in pre-processing. You could use it in lieu of the ISP. You can use it in post-processing. And where and when you would do that is going to be a function of the silicon that you have available to you, the memory or the physical size that you have available to you, and the power budget that you have. So there's not one right answer for doing image processing or signal processing. It can be that you take a dedicated image signal processor, like many companies are offering, and that works best for you, but it has certain limitations. Or it could be that you do use a GPU, and you can use them in conjunction as well. One can augment the other. I'm getting ahead of myself, sorry. So that's basically what I'm trying to talk about here, is that the choice is whether you go from dedicated hardware to a multi-core or a GPU approach. And it's the combination of flexibility that you get. The GPU fills in a big gap of this. In other words, it used to have extremes where you either build a dedicated processor to it, or you tried to make the thing work on a multi-core, say, x86 CPU or an ARM CPU. And now what the GPU does is it branches this, and it branches it in such a way that it takes out the hard breakpoints, so that you can blend into some of the functions that you might do in a dedicated processor, and you can blend into the functions that you would do in a multi-core CPU. And the blending is basically a workload decision. Where can I get the biggest bang for the buck in this heterogeneous environment that I have of these multiple processors? And that's what OpenCL does for you. So just to, is that going to work? Yeah. Just to reacquaint you with the, oh, I like that scintillation. You can see the difference between a low-res image, that's what I'm trying to portray here. The difference between a low-res image and a high-res image in this histogram here. And think about the histogram, think about the horizontal axis of that histogram as being the opportunity for parallel processing. Think of that as being the SIMD of what you would be doing with image processing if you were to employ a GPU for the functionality of it. It's just another way of trying to visualize the spectrum of choices that you have. And the other thing to think about is that the flops per watt per square millimeter of silicon per dollar. This chart pretty well represents that metric, if you will. You're going to get the most flops per millimeter of silicon per watt per dollar on a GPU than you will from anything else. Now, you might not get the most speed. And I'll give you a quick example on that. I remember I made the example of how we used to do transcoding on a CPU, and then we moved it to a GPU, and it really was fast. Well, Intel, starting with the 2 generations back, I can't remember the name now, processor, they were getting beat up in the market because the CPU just wasn't doing transcoding as fast as a GPU could. Intel wasn't going to have a GPU. So they built and embedded, because you can do that now with the shrinking transistor size, a dedicated transcoding processor, which is extraordinarily fast. So if you've got, that's what I'm talking about, if you've got the allocation of silicon, you can build dedicated processors that will beat any programmable processor. I think anybody here knows that. And so that's why the GPU will give you the best overall result in terms of price, watts, and powers, and so forth, but you can always beat it in one parameter or another with a dedicated device. Now, the workload that you have to deal with varies by the application that you are trying to satisfy. If all you're trying to do is sense something moving, say in a security camera, for example, that's a pretty easy problem. If you're trying to sense something moving and discriminate about what it is in terms of body shape and or distance from you and possibly even color, much more complicated. And if you're trying to increase the resolution to the point where you can see the tip of my finger or the shades of my iris to do identification, now the problem goes up. And that's an exponential differentiation. And as you run that model, as you move across these applications, the need to get an answer goes up exponentially also. I can't wait for 2 days or 2 hours or 2 minutes or even 2 seconds to have an answer that someone or something is pointing at me. I want that in 16 milliseconds. That's how fast I want that. And to be able to differentiate that finger coming at me in a partially lighted room, let's say, requires a lot of flops to do the processing. And that's where the GPU, again, comes to the rescue because it can process all that for you quickly. GPUs come from a variety of people. Oh, please let me, oh, phew, I was afraid I didn't have imagination on there. That'd be a faux pas, wouldn't it? So anyway, those are the primary suppliers. There's actually quite a few more that are making GPUs. This is just the top ones, and Intel and Win and so forth. So there's a lot of sources of GPUs that you can choose from. And where do you put them? You put them in all of these things and more. I was thinking about autos when Jeff was up here talking about where do you get new members and so forth. And I just got this random thought about how many cameras looked at me today coming down here. And I came up with like maybe a dozen. The first one that I think of is I drive across the Golden Gate Bridge to get here. I live in Marin. I thought, well, Golden Gate Bridge, if you haven't been on it for a while, is pretty cool right now because you just drive across it. And it looks at your license plate, and at the end of the month, you get a bill. You drove across our bridge, send us money. So that's one camera looked at me. I then went into a traffic maze. There were 3 cameras looking at me. Now, those cameras could do two things. Number one, they could look at me and see if I'm somebody that's a person of interest, or they could do what they're designed to do, or what they're theoretically designed to do, which is measure traffic flows. Where's all the traffic? What should we do with the traffic lights? What we should do with the lane movers that we have to move around to redirect traffic? Excuse me. Then I came down and I was driving down 280 and trying to watch my speed, and guess what? There was a cop, and he was taking my picture. Fortunately, I wasn't going too fast this time. Then I pulled over, and I just really, really wanted a cup of coffee, so I pulled over, I got a cup of coffee, walked in the store. There's a camera taking my picture. So everywhere I went, possibly into this building as well, I was having my picture taken. Something is processing that data, and I'm a pretty complicated looking thing, so there's going to be a lot of processing involved. Now, I hope that the bridge and the traffic flow and the cop and the coffee shop and this company aren't mingling their databases. So getting in a little bit more detail then. So the dual ISP, multiple ISP, I don't know if I need to explain this. ISPs? Jeff, hello? I do have to explain it? Okay. All right, so image signal processor is it's a complicated thing, and it's actually not tightly defined thing. It can start out with a simple image capture. In the old days, it used to be an A to D converter. Today, everything is already D, so we can move things along a little bit faster. The next step would be to go into some manipulations of the color. We'd go into a lookup table, color lookup table, and that's where we would make adjustments with regard to how we were going to process the image. Then we'd actually do some processing, because images, although there's a lot of pixels in them, they're not all valuable, believe it or not. There's a lot of redundancy, and so now we'd have the opportunity to do some compression. And then after we did the compression, we'd probably run it through yet another lookup table. And all that type of stuff would go on to build what we call an ISP. In the early days, and perhaps still even today, there was a big discussion trying to get these things figured out as to how much of the ISP should be into the sensor to reduce transport time and signal processing, and how much should be external. And that's a line that kept moving around, and Moore's law moved that line for us. And basically what happens is that line would move from where the processor-sensor interface is and where just the ISP is, on the basis of where were we finding a bottleneck and where were we finding manufacturing problems. If we couldn't get the yields by putting the processor on the sensor, then we'd take the processor off the sensor and put it into a dedicated ISP. That discussion kind of still goes on, but it's sort of settling out now. And putting the processor up next to the sensor is proving not to be the way we're going to go. Might totally shift back again. After we got the ISP figured out, then we had to figure out how to process the data. And that used to be a really horrendous thing. There used to be a lot of proprietary approaches for it. Everybody had their own solution on how to do it. In the early days of image processing, when systems were this big, that's what was the secret sauce of one image processing company versus another. Today, that's settling out. And the way that's getting settled out is by having open APIs. And Cronus, who is the champion of open APIs, and Neil will be talking to you more about it. And if you don't know who Cronus is, I hope Neil will take a little time to explain the organization to you. Several people here are members of it. But anyway, so Cronus has delivered open APIs to us, and that neutralizes the proprietariness and makes it possible to run the same app on multiple platforms almost anywhere in the world, almost on any machine. That's a big, big plus for us. Then there's another thing, which is called OpenCV. Now, OpenCV was largely supported, some people say created, but that's not entirely correct, by Intel. A lot of the work for OpenCV actually came out of the University of Washington, which was in turn sponsored by TI. And what happened was these great libraries were built on algorithms for dealing with various image processing problems that we would have. Color balance, motion detection, shake, rattle, and roll, lighting. There's probably there must be something close to 300 different little subroutines in the OpenCV library, and it increases all the time because it is open. And so anybody who can develop a really clever algorithmic solution to an image processing problem is invited to contribute it to the OpenCV community. That's the good news. Bad news is it hasn't had a very tight definition with regards to its black boxedness. And just, take you back to your freshman days. Black box is basically input, function, output, right? And you have definitions as to that, and inside is the magic. Maxwell's demons in there. And so OpenCV started out with pretty nice tight definitions, but like any open organization, clever people are going to come up with extensions for it. And so the net result is that we have pretty much of a zoo in OpenCV now. So managing that is a major task. And here again, stealing Neil's talk, OpenVG tries to deal with that. So one of the things that you want to keep in mind is that if you like the OpenCV library, you have opportunity to execute that on a GPU, and you have an opportunity to access it through OpenVG, an open for free standard. And that means that going forward, developing products for image processing just got easier. All right, so why? Oh, somebody said that mobile is the big thing. Oh my God, is it the big thing? Yep. I mean, we are so in love with mobile devices, and why shouldn't we be? They do so much for us. So tablet SoCs, we think, our firm thinks, and several other firms like us think, that there will be hundreds of millions of those devices sold. When I say SoC, that's system on a chip. And a system on a chip today, from companies like NVIDIA, Qualcomm, customers of ARM, customers of Imagination Technology, Samsung, et cetera, people, names that you all recognize, I imagine. SoC, including Intel, by the way, and soon to include AMD. An SoC has a whole bunch of stuff. An SoC is the epitome of a heterogeneous processor. And it may have, and I'll say probably has, an ISP in it. It will have a pretty damn good GPU in it. It will have a pretty good CPU in it. It will have at least one, and maybe as many as 3 or 4 DSPs in it. It will have independent video scalers and color lookups. And it will have energy management or power management processors in it. All that stuff in one tiny little chip that you carry in a phone in your pocket that runs on a battery for a day or two. Incredible piece of technology. And they're being built by hundreds of millions of them. Same thing's true in smartphones, except now we're talking an order of magnitude greater. This year, it's forecasted that we will ship 1.5 billion smartphones, or mobile phones, I shouldn't say smartphones, mobile phones of all types, feature and smart. They all have SoCs in them. They all have some level of GPU in them. Several of them have an ISP in them. That was the forecast. So here's, I'm wrapping up here, coming into the home run. What would we do with all this stuff? Well, AR, augmented reality, that's one of the big exciting areas. The opportunities that AR offers us are just astounding. The translator that we all saw on Star Trek, where every alien could speak to every other alien almost instantaneously, in English, mind you. I thought that was convenient. Well, we now have something pretty close to that. We now have, with AR, the ability to read a street sign or a menu and have it translated for us almost in real time. And we also have the ability to talk to it and have it talk back to us. We can get the machine to tell us how to say, "Good afternoon, and I'm so sorry I bumped into you" in Japanese. So we're getting very close to being the Star Trek realization. In cameras, DSCs, digital still cameras, in phones, in machine vision, security, all of those are image processing applications that can benefit, will benefit from parallel processing, because all of those applications are increasing capture resolution, and they are increasing color, and they are increasing frame rate. So you've seen the pictures where, it cracks me up, they still say, "Go get the tapes from that security camera." not tapes, who has tapes? But they go get tapes somehow. And they show these blocky, black and white pictures of a guy walking across, and they say, that's him, right? Well, that's 1990 stuff. Today, if you see a security camera footage, and it's not on tape, you'll see high-resolution color in a well-lit area. And the identification possibilities are extraordinary. PSA, as one example, has, next time you go to the airport, look up. And look for little black domes, and look for easy-to-spot cameras. And you'd be surprised how many cameras are looking at you as you take off your shoes and go through the scanner. They're not just measuring your body, they're looking at you. In a year's time, 2 max, the ability to pick out facial features, identify people in real time, so that if a person is a existing or potential terrorist or an escaped convict or a dad that didn't pay his alimony bill, before you're able to get your shoes back on, there's going to be a guy coming over to you and saying, excuse me, sir, could we talk to you? That's the kind of question you don't say no to. Yeah, please, I'd like to talk to you. That's coming. That's here now. There's experimental sites already doing that for us. Well, okay, you know about Connect and Leap, and there's 5 other companies that are building these things. In 3D scanning an image, I didn't bring my phone, but let's pretend this is my phone. In 3D scanning image, the next, let's see when this is going to happen. Probably by this time next year, I was playing with the prototypes recently, probably this time next year, we will take our phone and go like this. And what we will capture is not a panoramic video. We will capture 3-dimensional, geometrically accurate data that can then be used to construct a model of this in a computer, that if I wanted to make this into, let's say, a scene in a game, I could do that. Or if I wanted to make a replica of you in a 3D printing machine, I would have the data for doing that. And I'll be able to move that fast with my phone. Or I'll be able to play a game on it. So there's several companies that are involved in that, and I'm sure you read about Apple acquiring a company called PrimeSense from Israel. PrimeSense was the first sensor array that was put into the Microsoft Kinect. Did I put, oh, the other thing I forgot to put on here, sorry, intended to do it, was automotive scanning. Let me go to the next one first for focal depth compensation. Lightor and Samsung, they're both doing experiments with that. I think you know about Lightor. Lightor uses a field array. It's basically a lens that looks like a bug's eye, and it looks at you, or whatever it's looking at, through multiple focal lengths. And the net result is it creates a virtual cloud of you. And so it's got all these different rays coming at it, and it's stored. Think of it as being stored as 3-dimensional image. And then once you have that, you now have the ability in post to change the focal length. So if I'm in focus now and that's not, and you took my picture with this camera, you would then have the option of putting me out of focus and get that, or putting up here in focus and get that. And so it gives you this terrific corrective capability and the ability to have multiple images of the same scene. And so that's a technology that's now with us. Guess how they do it? They use a GPU, because that's the only way you can deal with a cube of data. There's just no other way to do it. ISP can't do that. The other thing that is coming, and this is coming really fast, is the cameras on your car. We'll have cameras on our wing mirrors for keeping us from drifting off and crossing lanes. We'll have cameras in the front, actually they'll be on the back of the rearview mirror, looking forward to keep us from driving into the car or the person in front of us. The wing cameras will also be looking for people. And there will be at least 1 and probably 2 cameras looking at us to see if our eyes are open, because it's very important that your eyes be open when you're driving. So all of those cameras will be running simultaneously, spewing out data. Guess what's going to process all that data? GPUs. The GPUs are already in the cars. They're already dealing with stuff like this, and so it's just going to be another application and more GPUs for them. One of the companies which I'm suggesting to Jeff that he consider as a member for this organization is a company called TrueSight. And TrueSight does HDR. They're not the only one that does HDR. Everybody does some form of HDR. TrueSight just happens to do it the best. But HDR, as you should be aware, and if you're not, I'll just go quick tutorial on it. It stands for high dynamic range. High dynamic range is what we have. We have something like 10 to the 27th dynamic range in our eyes, which allows us to look at the moon and look over into a dark shadow and see stuff, and then walk into a bright room and still see stuff. And we weren't turning any knobs when we did that, right? That's all happening automatically for us because we have perceptual high dynamic range. We don't have high dynamic range on our things. This thing right here and all the things that you guys are looking at have 8-bit displays. You can't have high dynamic range with 8-bit. So what do? Well, we have to shift. So we can either take the highs or we can take the lows. And we can zonal it. We have highs in this corner, lows in this corner. My favorite example of this is a scene inside of a church. And the church has tall windows and lights streaming in, very, very bright. And there is a little person sitting in a dark corner. Now, if you look at that in real life, you'll see the person, you'll compensate and deal with the bright light coming in, and you'll see everything else. You look at it on a computer, and you have to choose, do I see the light, or do I see the person? Because if I see the person, I got to kill that light, otherwise it's going to blow out my screen. But if I want to see the light, then I have to kill the person. And so if I could zone that, I have the window here and the person there, and change the gain of where I'm looking, then I'd have a quasi HDR, and it is quasi because these screens just aren't good enough yet. They're coming, by the way. 12-bit and 14-bit screens are coming. Finally, the bionic eye, which really gets me excited. Jeff said, what are you talking about bionic eye for? Have you seen, oh, this is the guy that invented AR glasses. It's a side story to this. I don't know, do you guys know this guy? Do you know about him? Do you know his story? Well, he's been wearing these things since 1977, no joke. It didn't always look this good, by the way. He's worn them for so long that he has become dependent on them. He actually has now a dependency problem. True story, he walked into McDonald's in Paris. That's a high security area, right? And they had a total meltdown, pissy fit about him wearing these glasses. And they came over and they said, take your glasses off. He said, I'm sorry, I can't, but I'm, I have vision problems. Blah. They said, take your glasses off. And anyway, long story short, one of the attendants decided to take the glasses off for him. Turns out he had a couple of wires sticking in his head. It hurt. He's suing McDonald's. They're saying it's a big misunderstanding. And the poor guy, I mean, it's kind of funny looking there, but he was now visually impaired because he had depended on these things for so long and was used to seeing that type of thing that he really needed help getting himself stabilized and sitting down. So that's the dark side of AR. But what I wanted to show you, oh, okay, more AR. I guess I was going to talk more about AR than I did. Yeah, I'll give you my little joke. Somebody was talking about Blackberries. I made this thing up about what I called the Blackberry roll. And the Blackberry roll was where people who really wanted to pretend that they were paying attention to you, but were really more interested in their Blackberry, would put it down there, and they go, yeah, I'm really paying attention to you, yeah, and then they roll their head down and Blackberry roll. I think we've all done that, or at least seen it, right? Well, now we have the new one. Now we have the glasses stare. Watch people walk into a wall. Yeah, I don't know if you guys have played with glasses or not. I'm amused by them, but I don't see them as being a great solution. And the other problem is that when you're not looking at the screen, you get this annoying peripheral little blue light, that makes you do that, makes me do that anyway. This is where we're going to go with AR. Now, I don't know if I have it. Yeah, I think we do have it. There's a better AR example, or the best. Yeah, here it comes. These are real things. This is the most sophisticated AR/VR system in the universe right now. And it's what, and you notice that there's an airplane reflected on that because it's almost opaque. And pilots of the new multi-nation strike fighter F-35 wear this, and inside that is Tony's head mask that you see. It's filled with data, totally filled with data. There's some alleged, I'm saying alleged because I can't prove it, it's in there, and if I could prove it, I probably wouldn't be able to admit it, I knew it. But the Air Force has been working for some time with regard to blink control. It's a problem that Google Glasses has as to how to differentiate on blinks. What do you do with a blink? So the Air Force has been experimenting on this for some time because things are happening so fast in these planes that how do you possibly get a quick enough reaction to do something with your hands? The answer is you can't. There's just 18 milliseconds involved there that you can't overcome. So you blink. And I just shot 3 missiles at you. Now I'm firing my machine gun at you. Right? You can imagine all the problems with this working properly, right? Damn, I got this itch. Oh, sorry! So anyway, I'm saying alleged, like I said, I can't really prove it. It's probably a top secret thing, but I know that Wright-Patterson Air Force Base has been working on this thing for about 15 years. I've done a little bit of work with them on it. It's fascinating technology to think about. Part of what came out of that Wright-Pat work, by the way, just a little sidebar here, was the laser writer that writes directly on your retina. And that's a very, very effective display system. Some people are afraid of having a laser right on their eyes, but it's not dangerous power levels. Oculus, everybody know what Oculus is? Oculus is going to be probably the first successful commercial consumer virtual reality system. It's pretty crude right now. They're just now experimenting with HD resolution. So right now they have something a little bit better than VGA, but not HD. Enormous amount of problems to solve with this. Not the least of which is the response time that I mentioned to you, how fast you move your head before how fast the image catches up with you to know if you've moved your head or not. Incredible amount of problem solving goes on to this. This is going to be a consumer product for games that will sell, you can probably figure maybe $200, 3 max when it first comes out. But keep your eye on this. I don't recommend it as an investment opportunity, but keep your eye on it for technology. Lots and lots and lots of GPU compute there, lots. A gazillion amount of GPU in that helmet. Scanning devices, Connect Leap, I've already covered this. This is just the Connect block diagram. I think you guys probably understand that now. That's what it looks like when it's put in a box. Visualize that, literally, in the top of your phone. You know where your camera is now? Just visualize that you have that in your phone now, this time next year. These are the 3D scanning things I mentioned to you. So that's one of the models that looks like it, and you can see what happens there. In the CAD industry, computer-aided design industry, and AEC industry, they are now using scanning like this, which also is used for reverse engineering. When you are in the CAD industry, drawings are critical. And a thing called BIM, Building Information Management. And there's a lot of stuff that's built. Think about your home, for example, or it was built a while back, maybe 100, 200 years ago, that there's no drawings for. So they take devices like that, and they go in, and they put them on a tripod like this, and they basically sweep the room. They create what's called a laser cloud, that then gets processed, and you create CAD drawings from that. It's even getting to the next level where they're scanning items, like, say, bridge elements. They get a picture of the bridge element, which is a scanned 3D geometrically accurate model. They ship the bridge element, and they scan it again at the other end, and they look to see if anything happened to it in transit. And things happen. Pieces break, it gets bent, something happens to it. But now they have a before and an after geometrically accurate model of it, and then the lawyers get to talk about what happened in between. That's now being done commonplace. Sensors, GPU processing, commerce. Almost done. Okay, so that's light tour. I'm not going to spend too much more time on this. I think you guys probably have that. I really wanted to talk to you about the bionic eye. There's the bionic. Everybody know about this? Anybody? This is science fiction. So, that face. At the bridge of his nose is a camera. Behind there is a representation of the person's eye. You wouldn't see that. See that big black thing on the side? That's a impinger. It's a RF impinger. Take a subject who is partially blind, maybe even totally blind, and literally embed in the head, right in front of the optic nerve, an array of pixels. And that's now in your head and underneath the skin. And then the big black thing, like say through RF, communicates with that, sending the information coming from that camera. Of course, you know that a GPU does all that processing. This is what it actually looks like. It's been FDA approved. This is the device. You can see the thing there. That's just the processor and the power supply. That's where the GPU is. And there's the thingy that goes in your eye. This. That's hitting your optic nerve. So it sounds perhaps a little strange, a little bit, weird, but think about being partially blind and being able to get your sight back. And this is good enough now. It's pretty low res now, believe it or not. It's good enough that a person who was partially or almost completely blind can walk into a street and see the crosswalk in the street. That's pretty important. Obviously, you can see a car coming. Other people, not quite good enough to do facial recognition or read a newspaper or something like that today. We all know about Moore's Law, right? 5 years from now, we certainly will. The suggestion is this could be the first step to augmentation for enhancement, not just repair. We have pretty damn good eyes. Suppose we can make them even better by having these things stuck in our heads. And that's it. Probably ran way over time, I'm sorry. I get passionate about this. Oh, buy my book.
John, stick around for questions. I'm sure there are going to be a few questions. Who has a question for John? Ken.
Yeah, please. Oh, can you use the mic?
What's your thought on the using the GPU for 3D processing? Because 3D processing is quite different from rendering, which GPU is great at. You got a bunch of XYZ points, and a lot of times you're processing group of point. It's a point cloud processing, which is very different from what the architecture was originally meant to.
It's being used right now. I mentioned to you about the scanners. That's all point cloud, and that's all GPU processed. Remember I told you think about data as being in a cube, right? So it's basically, a point cloud is basically voxels. Everybody know what voxels is? Volume pixels? And a volume pixel is just basically a pixel that's got 3 dimensions of data on it, X, Y, and Z, plus color and time, so it's 5 dimensions. And you have all these things, and really think about it like being a crystalline structure. And you process that. Today, we process it on a slicing basis like an MRI picture, chunk, 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 chunk. If your question is, could we process 3D voxel data simultaneously in 3D like we do in 2D now? The answer is absolutely. It's just a matter of accessing the data. So where the data is stored, if the data is stored in a XY constructed memory system, then we have certain limitations. But there are memory designs that exist that are 3-dimensional. In fact, memory on top of CPUs to get higher density are coming to do that. So today, we're not doing 3D because of memory access, but we will 2 years. Does that come close to what you were asking?
Yeah, that's about what I was expecting.
Oh, okay.
It's not quite there yet, I don't think.
No, it's not, but the limitation is the memory. Now, the one way around that is you stack up memory, right? So if you can only read X, Y on one memory chip, if you have multiple memory chips, now you could read Z. And that's a packaging problem, not a processing problem. Back there, John?
John, sort of related to that, with the proliferation of these devices, is storage keeping up?
Yes, remarkably yes. Aside from the spinning stuff, which has had an extraordinary curve in terms of density and price going down, we just bought, this is no exaggeration, we just bought a 10 terabyte disk. Guess how much? $200. $200. Think about the first disk that you bought, right? But going forward, there's new crystalline devices that can store hundreds, literally, of terabytes. They're being made round. I don't know why. They're not going to spin, but they're being made round. They'll store hundreds of terabytes. They will never die. All the magnetic medium that we have on tape and stuff like that, going to die. The stuff that we have on spinning disks, going to die. Flash memory, going to die. Right? This crystalline thing will not die ever. The problem then becomes, okay, if this now becomes our archival library with this enormous, and this is first gen, right? 100 terabytes first gen. Are we going to have readers? How many of you have floppy disks that you can't read anymore, right? So that's the next problem in archiving is, well, you can't just save the data. We have to save the machine to read the data. Did you have a question, sir?
No, you asked the question, I answered yes.
Oh. You have floppy disks? The first book I wrote, I still have on 5-inch floppies. I'm thinking, why the hell am I keeping this? You know, I don't have a floppy drive.
Any other questions for John? Okay, John, thank you very much.
Very much.